Well, hello, this is the video for Chapter 14, Future Mathematicians, in the book How and Why Homeschool Math Can Be Vastly Superior to Public School Math. And I'm the author, Craig Hain. I'm the chairman and CEO of Triad Math Inc. You can learn all about me at my website, craighain.com. Now, in a certain sense, this may be my favorite chapter in the book, although it will be quite difficult for most non-mathematicians to truly follow, but this will give you, a layman, a taste of mathematics and what it's about and what we should be doing for our students and our future mathematicians. So really this chapter is for parents or teachers who might have a precocious math student who might wish to consider a career in mathematics. And as I said, this will not be a particularly easy chapter, but you might enjoy it. Just sit back and listen to the ideas and the words and the terms and enjoy. It's going to give you an idea of what we really should be doing for our relatively few precocious math students that are potential mathematicians. And of course, we're not doing that at all. We are completely and totally shortchanging our best math students in our public school system. And for that matter, our homeschool system too, but it could change. The homeschool system is probably the one place where we could rectify this. And I ask you this, what is more important to us as parents and educators than delivering an adequate education to our students? And that means what they really need. Now, I believe very few things, and if you've got a precocious math student, then this is what I think you should be doing. Now, of course, up until this 21st century, the best we could do is what we're doing today. Batch teaching math in our massive school factories, what I call a second wave approach. And today, of course, with our modern technologies, we can deliver what I call a third wave type education I've been talking about in this book. And it's vastly superior in all ways to our current second wave system. It is, of course, based on spike pedagogy and all of that and proper topics. Now, what does this mean for our best and our brightest math students, the ones that could become mathematicians? And I might tell you this may be, in some sense, one of the most important things that we can do for the long-term health of our society. After all, one math genius can literally transform the world. Somebody like Einstein or Paul Dirac or Richard Feynman, to name three of the brilliant physicists who was based on math in the 20th century. And I won't mention the math names because you probably will not have heard of them. People like Emil Artin, J.P. Sayre, and people like that. More recently, Terence Tao. Just imagine, for example, that we didn't have youth sports activities. Suppose we didn't have any little league or junior football. Suppose that our athletes couldn't start playing ball until they were in their late teen years. How good will they get at sports? How good will our best athletes be? If you look at the background of our very best athletes, they started when they were very, very young, usually by dedicated parents. Look at Tiger Woods. When did he start playing golf? Very, very, very young age. Would he have been a Tiger Woods if he had not started playing golf until he was, say, 18 years old? I guarantee you not. The same thing's true for music. What if you didn't start teaching music to a future musician until that person was in their late teens or 20s? Again, crazy. You wouldn't even think about it. Well, that's what we're doing to our mathematicians today, our future mathematicians. We're shortchanging them terribly. Now, I want to describe for you some of the concepts that we ought to be teaching our future mathematicians very early on. And this can be done starting very early in their life. It'll depend on student to student, but it can start really quite early. Now, you're going to just not understand a lot of these terms and what I'm talking about. I'll describe them very, very generically. Well, first of all, we start teaching our students what's called the axiomatic method and rigorous ways of dealing with math. Now, that starts with Euclidean geometry, and we do a little of that now in high school, but you can start this quite earlier. What it means is the axiomatic method is where you start with a set of undefined terms, you make assumptions about them, they're called axioms, and then you prove theorems using Aristotelian logic. Now, we do this once we start training our advanced theoretical mathematicians, starting with number systems. We start with the natural number system, the counting numbers, 1, 2, 3, 4, 5. And we have an axiomatic system called Peano's axioms. Now, that's not the musical instrument, that's P-E-A-N-O, and that's named after an Italian mathematician by the name of Peano. And then we extend that to the rational numbers, which are fractions, then to real numbers, which are all infinite decimals, then to complex numbers in the two-dimensional plane. And I discuss all this heuristically, as you know, in Tier 4. But I don't do it rigorously because they're not ready for it yet. Now, you don't want to start rigorous math until you've taken them through the first 6 tiers. And by the way, a really bright student will get through the first 6 tiers by the time they're, who knows, 10 or 11 years old. Then we have the hyperreals. Now, that didn't happen until the 20th century, and so on and so forth. And this is just a few examples of axiomatic systems. Then we're going to show our kids how you make math models using these various structures. The modern math structures are called, for example, topological structures, which is the way you study continuous functions. Then algebraic structures like groups and rings and fields. Hilbert spaces. This is an infinite dimensional version of n-dimensional space, and this is what is used in quantum theory. Now, I used to teach all these things when I was teaching seniors and graduate students when I was a professor. So I've taught all these subjects, but usually by the time I got around to teaching them, the kids were in their late teens, early 20s. And quite frankly, it was getting late. I didn't learn a lot of these things while I was in my 20s. I wish I'd have been taught all this stuff when I was much younger. Then they have something today called chaos or nonlinear dynamics. Very important for science. Our modern models really you have to understand this to understand the limitation of our modern models. Very important subject, and this didn't become extensively treated really until the 1960s. Then there's something called spectral logic. Now, that is where you can take a proposition and assign it some truth value somewhere between 0 and 1. We use Aristotelian logic today, where everything is either true or false. Well, in spectral logic, you can have something that's half true, half false, 3/4 true, 1/4. And this, by the way, is the basis of many of our modern control systems. Now, I will tell you, spectral logic today is often called fuzzy logic. And I hate the name because it implies that it's, well, fuzzy, that it doesn't mean much. This is just as rigorous as Aristotelian logic, in fact, even more in a way. And it is extremely important in modern control systems. So you need to learn and by the way, it's not hard to learn. That's the nice thing about it. Then you need something called fractals in non-integral dimensions. And I won't get into that, but that is something that is not very hard to understand. And it's very important today in many of our math models. Now what's going to happen fairly early when you're teaching a student thing, you're going to talk about the concept of an infinite set, infinities. You know, like 1, 2, 3, 4, 5. How many natural numbers are there? Well, they're an infinite number. Well, that's true, and our ancestors knew that. There was such thing as infinite sets. They thought any two infinite sets were always the same size. In the late 1800s, mathematicians discovered, George Cantor was the mathematician, that you can have infinite sets with different sizes. In fact, what he proved in general was if you have an infinite set X and it has what's called a cardinality, it's a certain size of infinity, then if you take the power set of X, the set of all subsets, it is a bigger infinite set. And this is called the generalized continuum hypothesis. It's an amazing thing. And by the way, I learned this when I was probably a sophomore in college at Oberlin. And it really is something that makes you think very deep about math, because math is highly theoretical. Math, although it's used in science, it is very practical in that sense. Theoretical math is very, very theoretical. And infinity is one of the first times you run across it. Another thing that's extremely important in modern math is called the Axiom of Choice. We have many times when we can prove something exists, but we can't construct it. And this is because of the Axiom of Choice. And there's an equivalent statement called Zorn's Lemma. Now, this was named after a great mathematician by the name of Max Zorn. I happen to know Max Zorn. I was 2 doors down from him at Indiana University when he taught there. He came over with a great mathematician by the name of Emil Artin, who was a great algebraist at Princeton, and he brought Max Zorn over with him when he came to this country. Now, there's something called infinitesimals, and I use them extensively when I teach calculus because intuitively they're very easy to understand. Archimedes used them, Newton used them, Leibniz used them in the 1600s. Archimedes, of course, was an ancient Greek. But we couldn't make them rigorous in the 1800s. In fact, they got banned from mathematics. And then in 1966, Abraham Robinson was able to include them axiomatically, and they got back into theoretical math. That's quite a story in math. It's almost an embarrassing story because practical mathematicians and scientists and engineers continue to use infinitesimals from in the mid-1800s all the way through. They were banned from math. They're not in the textbooks today the way they should be because of what happened in mathematics. Now, what's the impact of modern math on science? Well, it's absolutely huge. Mathematics, these theoretical models, are then used as the basis for scientific models. And if you don't understand the math models, you can't understand the scientific models. And you can't know the limitations. For example, if you have a linear model of something, it'll be very predictable in its behavior. If you have a nonlinear model, it will be non-predictable. This was all discovered back in the mid-1960s. And we know now that many of our math models on complicated things are simply unpredictable. You simply can't know in advance or predict what the behavior is going to be. And that's what gives us problems today with our things like our climate models, just to use that, or our economic models. We just don't know what's going to happen in many respects. And that's something that a theoretical mathematician has to learn. You have to learn that fairly early on. That's what's behind black swan events, for example, and things like that, and risk analysis. This is what Nassim Taleb talks about. If you set up a model that has this kind of behavior, you're going to get very unexpected results. And these are just quite a number of the topics that I believe we should start teaching our children when they're really quite young. I'm talking about our precocious children. I'm not talking about most children. There may only be one child in 10,000 that really will benefit from this. After all, how many great football players are there going to be? Of all the people who play football, there's only going to be a few that are going to be great. Ditto for any sport. There's only going to be a few. But what would happen to LeBron James if he hadn't started playing basketball until he was, say, 17 years old? That's when he started. That's when they started really teaching him. Well, it wouldn't have been LeBron James. And that applies to any famous mathematician or musician. Well, the same thing applies to mathematics. Now the question is, what can we do about it? Are we going to correct this situation in the United States of America? Well, my favorite mantra is, man plans and God laughs. I personally believe we can do it. I think it can be done. In fact, I would like to be involved in it. Once we get homeschoolers really going, homeschoolers today, and get a large installed base, I plan to tackle this. These are the subjects I love and I would love to teach them. It's not for ordinary math students. This is not for 99% of your math students. It's for the ones that really want to become mathematicians. Now, is it going to happen? Well, that I don't know. You can't predict that sort of thing. When I started this whole thing 10 years ago, by 2011, I'd done the first 2 tiers of a 6-tier program. And I plan to continue on. I couldn't be sure it was going to happen. Well, now we're sitting here in 2019. The 6 tiers are done. You can teach your children now what they need to get STEM math all the way through calculus and differential equations, using the modern tool of Wolfram Alpha, using modern pedagogical techniques, online, very inexpensive. In fact, you can have a reasonably bright STEM student all the way through calculus and differential equations time they're 16, 17 years old. And they should be. Then they're ready to go into science and engineering. But math, theoretical math, that's another thing. And that's something that you would start a student on probably when they were really quite young. Is it ever going to happen? Well, I don't know. I think so. I'm optimistic. I hope so. But quite frankly, here's what I think is going to depend on. I think it's going to depend on what I call the homeschooler's tribe. I think it's how you're going to handle it. I cannot imagine public schools ever dealing with these topics. There isn't one high school teacher in 1,000 understand most of the things I just talked about. And I don't blame them, by the way. I mean, I learned a lot of these things after I got my PhD in math when I was 27 years old. So a lot of these things I learned while I was getting a PhD. Much of this I learned after that. I mean, I study math. It's kind of like a hobby, if you want to call it that. It's a labor of love, and so I've studied a lot of these things since then. But these are things that I wish. If I could have learned all these things when I was a really young man and a young boy and getting started, I don't know. Maybe I would have been a great mathematician. I don't know. Probably not, but I could have been. But I had no chance at all. Well, I didn't start this until I was in my 20s before I began to learn these things. And so no chance at all. Well, I think the Homeschoolers Tribe has got a chance to doing this. So I say bring on the math prodigies. If you know someone that you think is a potential math prodigy, I want to know about it. Because what I might even do is start developing these things while I've actually got one or more students to go through them as I'm developing them. It's good to have feedback as a teacher. And a lot of what I developed so far, I did it without a lot of feedback in the beginning because I taught so many students that I knew pretty much what to do and how they were going to react. But this would be something that would be a lot of fun. I mean, I don't know what it would be like to teach a 10-year-old or 11 or 12-year-old child infinity, the concept of why aleph null, the cardinal number of natural numbers, is less than the cardinal number of real numbers. That's a tough concept. To teach them the axiomatic method, to teach them a lot of the structures that we talked about. In fact, one of the most interesting structures that I've come across in recent times that I'm very interested in is what's called the E8 Lie group, the exceptional Lie group, E8. That is the most complicated structure in theoretical math as far as I know. And it may become the model that extends the standard physics models we have today. It's the kind of thing that people like Eric Weinstein and others and Lisi talk about. It's a fantastic thing. But you can't understand that until you learn a lot of these other things. And that's what our future geniuses are going to do. And if we can do this as homeschoolers, that'll be a fantastic thing. And I invite you to just think about that and what we can do about it. And I invite you, if you want to discuss it further, especially if you have a student you think might benefit from this, to contact me. My contact information is on my website, craighane.com. You can just call me and we can talk about it. So this is Craig Hain. You can tell I get kind of excited about it. I think it's a fantastic thing. These things are sort of the height of human achievement in the field of mathematics. It's kind of like the best music that's been written. It's the best, it's the best books that have been written. This is the, in my view, sort of almost maybe the crowning achievement of modern human thought processes. Okay, enough of that. I hope you enjoyed this chapter. I hope you enjoyed the book. There's one chapter left, chapter 15, on conclusions, and you'll be happy to know it's a very short chapter, and the video for that is only 3 minutes long. And so if you don't do anything else, watch the last chapter. And I hope that you are successful in training your students math, and I hope you're enjoying this, and I congratulate you for being part of the Homeschool Tribe. Dr. Dell or Craig Hain, I will see you hopefully now on another video. Have a great day. Have a great life.